I'm excited to see so many faces here. And for this workshop, we actually have a guest, a very good friend, an advisor for Superquantum. Dr. Yudong Cao is the head of Quantum and AI at iQuHACK, where he leads the development of quantum and AI solutions for clients across sectors such as national security, aerospace, and pharmaceuticals. He previously co-founded Zapata AI and served as its founding scientist and chief technology officer, helping translate cutting-edge quantum algorithms into practical enterprise applications. Trained as both a mechanical engineer and a computer scientist, he holds a PhD in computer science from Purdue University and completed postdoctoral research in the astrophysics group at Harvard University, with widely cited work on algorithms for noisy intermediate-scale quantum devices. That's what we want. So please welcome Dr. Yudong Cao. Right. And for this workshop, we will have a lecture-style workshop. So we will be using Blackboard mostly. Enjoy.
Thank you, David, for the introduction. So this is going to be a chalk talk, and before I get into the details, I just want to make some broader remarks about the subject, which is quantum compilation and T-count optimization. So more about what T-count means later. And this is one of the subjects in quantum software. And if you've been following quantum computing in the past few years, maybe you have seen some very impressive press releases from different companies. You just heard from IonQ, but there are also big techs like IBM, Google, etc. There's a lot of progress in quantum hardware, and a lot of these companies have projected their future well into 2030s to say that they can build, the hardware is only going to get bigger and bigger. There's a lot of progress in quantum error correction. A lot of the error correction machinery actually uses what we're going to talk about. But the question is, if we had a perfect quantum computer tomorrow, as of today, there's no mature software infrastructure that will actually support running it, at least not in the way that we think about how to run things on a classical computer. Today, you can write a code script in C, and you can just call it GCC, and then the rest is taken care of. This is far from the case with quantum computing. We are far from the realm of just writing some code, and then the compiler would just take care of it, and then in the back end, somehow, magically, it's run. Today, we are very much worried about what happens to a qubit during a computation, how are qubits connected, how do we entangle them, what is the sequence in which we apply these operations, and we worry about the very details of the physical process of what happens to qubits during computation. So that's the sort of a snapshot of how much work there's more to do, and hopefully that you'll find that interesting or exciting. And as quantum hardware becomes more and more mature, there's going to be more and more demand for people who know about software. And I think this is why today this topic is even more exciting, because I'm glad that you all are here, that you all have some interest in quantum software, because this could be, you could say, one of the underappreciated topics in quantum computing, which is how do you actually take some logical circuit, logical quantum program, and very efficiently compile that to a backend. So since we're talking about individual qubits, we are reasoning about two-level systems that admits this kind of vector form. Right? You probably learned from your linear algebra that the state of a qubit is essentially a combination of a pair of amplitudes. And then naturally, everything that happens to a qubit can be written in this 2x2 unitary matrix. So it's unitary because it's quantum mechanics. And the way we think about 2x2 unitary matrix is through a basis. So it's kind of like a coordinate basis. With vectors, you can expand a vector into a basis of orthogonal vectors. You can also expand a matrix into a basis of so-called orthogonal matrices in some sense. And some of those very useful matrices, and for those of you who study physics, you probably have already imprinted this in your mind. And I think if you're a physics graduate student, it's almost a requirement that you memorize these three matrices, or with some constant factor in the front. So these three matrices describes the space of possible 2x2 unitaries, which is the space of all possible operations you can perform to change a quantum state. So they're very, very important. So these are the Pauli operators. And this becomes the sort of de facto language with which we describe not only what happens to a single qubit, but also to n qubits, to arbitrary number of qubits. So as such, it's useful to define, for our purpose, a general idea of the kind of things that we can do to n qubits. So this is the n qubit Pauli group. So we can write that as p to the n, Pn, which is a group that's generated by x that's applied to qubit 1 to qubit n, and also z operator that's applied to qubit 1 to qubit n. Just as a quick show of hand, how many of you know what a group is? Mathematical concept. Okay, that's great. So this is the rigorous way to describe all the things that you can do, at least the basis of all the things that you can do to n qubits in terms of these basic Pauli operators. So now we have basically a language, right? We have so this is sort of the building block of all that's possible on a perfect quantum computer. And then naturally you can reason about what are the operations that we can define on top of this group. So a first idea is to say, if there's a unitary, if there's an operation such that for any Pauli operator, when I conjugate this element with a unitary, I return something else back into the Pauli group. In other words, if there's a unitary that preserves the Pauli group, then this is defined as a Clifford operation. So it's a special type of operation that preserves this, and you can imagine writing down a circuit with some very complicated pattern of gates, and people typically think about, let's say, if you have n qubits, then the cost of simulating this is on the order of 2 to the power n in general, because the two-dimensional Hilbert space, it stacks up exponentially because of quantum mechanics. But the nice thing about Clifford groups is that you don't have to, you actually don't have to take 2 to the n. You actually just have to keep track of some Pauli operators. So let's say you have a set of Pauli operators at the beginning of the circuit, and as the unitary gets applied, because the unitary preserves the Pauli group, so you know that you're never going to depart from the initial set. So whatever Pauli operator you pick at the beginning of the circuit, you will not have extra Pauli operator coming up as you go through this. So if a circuit is made up of all these nice Clifford operations, you actually don't have to go through this 2 to the n trouble to simulate this. You actually just have to simulate this with a linear number of Pauli operators. So this makes for a very nice property, that this makes the quantum circuit classically simulatable. So it will be classically efficient to simulate. And this is a very big deal, because this means that on one side, not all quantum circuits are special, in the sense that not all quantum circuits are just mind-blowingly complex. Like there is a certain set of quantum circuits that turns out to be not so powerful. So this is a very famous result by Daniel Gottesman, who is a founding researcher of quantum error correction and Knoll. So it's called Gottesman-Knoll theorem, that says if your quantum circuit is made of only these operations, then you can efficiently simulate it actually in linear time in the number of qubits. So these are, turns out to be a very limited set of operations, and then the question is how to actually make it more powerful, right? How do we recover this universality? So one side note is that the Clifford operation is not only not universal for quantum computation, but also that it's not universal for even classical computation. So here's something that we can. So let's play around with this and see how it works, right? So we typically consider a minimum group, so a minimum set of Clifford gates as a C0, Hadamard, S, and S gate. So Hadamard gate, just to be explicit, is a 2x2 operation, is a 2x2 unitary, and S is also a 2x2 unitary, and a C0, it's a 4x4, it's a 2-qubit operation. So these form the basic Clifford gate set, and then if you plug that into the Pauli operator, right? So you can make some observation that there's some nice connection between these Clifford operations and the Pauli operators. So they allow us to go back and forth between different, you can say, basis matrices. So if you conjugate X by H, you get a Z, and then you can sort of carry the H to the other side, and then you can conjugate Z and then get X, and then you can similarly conjugate X with S, and you get Y, and then S is diagonal, so it just commutes with Z. So one thing that you can play around with this is you have, for instance, a direct connection between these Clifford operations and Pauli operators. So, for instance, square of S is Z, and then if you plug in if you plug this into here, right? So X equals to H Z H. So this, if you plug this into this, then it's just H S square H. So in other words, you can actually do some classical computing with Clifford operation. You can actually combine H and S, and this gives you a bit flip, and then you have C0. So these two operations allows you to do some classical computing, but it's a very limited form of classical computing because you, as you can see, the operation of X, right, is just to flip the bits, or I guess in a more general notation, you would say it's an XOR operation, and then the action of C0, right, is so basically the Clifford groups only gives you the ability to do these to compute these linear functions. So XOR is basically just addition modulo 2. All right, so this is equivalent to XOR. So if you state with this Clifford gates, right? So if you state with this Clifford gate set, then all you can implement on the quantum computer is basically functions like, for instance, a Boolean function like g, x1, x2, x3, where it's an addition of these variables. So this is the only type of computation that you can do with Clifford gates, and so it's not even universal for classical computing because it only implements the linear functions. So actually, there's a result by Scott Aronson and others that you can make it universal by introducing a Toffoli gate. So basically, if you have C0 and X, right, these are your Clifford gates, and then if you add a Toffoli gate to your gate set, so those are essentially these 3-qubit gates, where if input is A, B, and C, the output is C plus A times B. So in other words, this is a nonlinear operation. So it turns out that if you include just a little bit of nonlinearity, if you include one gate that allows you to do this nonlinear operation, then this actually allows you to perform universal classical computation. So this is a result by Aronson. So this is if you're interested, you can look at this. You can look at this reference. Basically, it's a complete classification of like reversible classical methods. So that's pretty much what's interesting about Clifford gates. What you can do with them, and then the next question is how do we actually turn that into universal quantum computing? Right? How do we actually make it universal so that we can manipulate arbitrary n-qubit states? And there's actually infinitely many universal quantum gate sets, but I don't have infinite time, so I'll just pick a couple that's kind of interesting. Let's see. Universal quantum gate set. So the first one is actually Toffoli and Hadamard. The interesting thing about this gate set is that you only have 2 types of gates. So we already talked about Toffoli gate, right? So we know that it's a very powerful operation. Once you have it, you can do arbitrary classical computation combined with Clifford gate. But it turns out that you only need one of the 3 Clifford gates to make it universal for quantum. And this is, if you're interested, this is a result proven by Dorit Aharonov, who is a theoretical computer scientist who did a lot of work in quantum computing. So she has a nice proof for this fact, but other people have proven it as well before her. But I just thought her proof is a lot more elegant. So it turns out that you can do everything there is, or at least approximately universally on a quantum computer with just 2 types of gates. But for various reasons, the gate set that we're more interested in is so-called the Clifford plus T gate. So this T gate is defined as a so-called pi by 8 rotation, even though you see here it's a pi by 4, but we still call it pi by 8 because up to a phase shift. So if you extract a pi by 8 phase out of it, you can show that this is actually just pi by 8 of z, right? So it's just exponentiating the poly z matrix. So it's typically referred to as a pi by 8 phase shift. But we're going to stick with this representation because it's just easier to work with. So this T gate plus the Clifford allows you to approximate an arbitrary unitary operation to arbitrary accuracy. And there's something unusual about this. And first of all, it's not a Clifford gate, so it doesn't preserve the n-qubit poly group. And so one way to see this is that if you conjugate a T gate with X, so X is an element of the n-qubit poly group. This actually gives you, so basically you just plug this in and then substitute into X. So I'll spare you the algebra and just write down the result that this is X plus Y divided by square root of 2. So point is that you started with one poly operator and you end up with 2. So imagine if you had a circuit, right? Imagine if we did this, if we played the same game as here, where at the beginning we had some poly operators, right? And then we just want to go through the circuit conjugating these poly operators with these unitaries as a way of keeping track of the quantum state. If we play the same game, then you can see this is quickly going to blow up in our face because let's say if we're hit with a T gate right off the bat. Imagine if this is a circuit, right? This looks like a very simple circuit. It's circuit of depth 1. But imagine if we were trying to play this game here, we're going to end up with, for instance, let's say we have a P1, which is x1, x2, all the way to xn. And then we conjugate this circuit, right, with t to the n. So this is the first layer. If we conjugate by this, then we're going to have essentially an exponentially many. We're going to have these terms. And we're going to have 2 to the n terms just from one layer of the circuit. So it's very clear that we won't be able to play the Gauss-Neo trick here by just keeping track of these poly operators. So T-gate really kind of breaks this very nice picture that the circuit is efficiently simulatable. But it's a good thing because that means you truly need a quantum computer to execute these operations, right? There's no classical shortcut for doing it. So this is the case that we want to focus on with Clifford plus T, and we should. So it's easier for now to consider this special case. So the special case where the whole circuit is just built from C naught and T. So C naught is a Clifford gate. So we're restricting ourselves to just 2 gates, and this sort of simplifies the analysis and allows us to reason through different properties, and you'll see there's some very interesting pattern. There's a very interesting structure that comes out of this, and there's also a segue to maybe what the superquantum team is working on to automate some of the mathematics. Yeah.
Is it still universal if we don't have the H and S Clifford?
It's I actually don't know if it's universal. My suspicion is that it. I don't know actually. I think it should still be universal because this essentially means we're not working with Hadamard. So we are limited in our ability to do single qubit rotation, but at the same time, we have T gates. So I'm not sure if it's universal for arbitrary unitary, but it's expressive enough to capture what you can do with Clifford Clifford gate minus minus the Hadamard, basically. So we're actually following. So the reason why we chose this special case was because in the literature of quantum compilation, the researchers who have done this line of work somehow picked this as a special case to start, and then they added the Hadamard and to be part of a broader machinery for compiling arbitrary unitary into Clifford plus T. So also, if we have time, we can talk about, in general, what is a sufficient condition for a unitary to be representable exactly with Clifford plus T. I think as long as the matrix elements fall onto some kind of integer ring, you can show that the unitary can be exactly represented by Clifford plus T. For now, let's start with the special case where let's say the circuit is just directly only built from C naught and T. And one thing that sort of falls out of this, and I think will be interesting to know, is that if you take the square of the T, you recover the S, right? Because it's pi over 4. You square it, you get S. And then because the square of S is Z, so that means T to the power 4 is equal to Z. And then T to the power 8 is the identity. So that means T to the 7 is T dagger. So basically, there are all these powers of T that can give you all kinds of different gates that we have covered so far, and this fact will come up pretty handy as we go further into the compilation. And we previously discussed how C naught and X gives you only the ability to implement linear functions. So a network of C naught and T naturally implements unitaries of this kind of form. So if you had n qubits, a unitary applied to a computational basis state of n qubits will give you generally this form where there's some function phi of these bits, and then there's some linear function. And this linear function is not too much of a concern. You can very much remove it by using C naught to uncompute this, and then basically you recover a diagonal unitary. So in this special case, we basically assume that the unitary is diagonal. So for any input state, you get a phase factor. So let's look closer at what this phase factor, because this phase factor has a lot of interesting structure that allows us to reason about it and then hopefully discover equivalent and more efficient implementation for it. So consider this example where we have 3 qubits and we have a C naught here. We have a C naught here, and then we have a T gate here, and T dagger here. So this circuit, and so the first part of this is completely classical. So basically, if we look at here, right, we have x1 plus x2 modulo 2, and then we have here x1 plus x2 plus x3, right? Because we're just taking this result and adding it here. So we're just populating the logic of C naught here, right? So we computed these classical linear functions. So that's the function g, and then the action of T gate here, basically it's a diagonal gate, right? So it applies a phase only when you have only when the bit is 1. So implicitly you can say the t, so it will do nothing if the input is 0, and then if the input is 1, it will give you this pi over 4 phase. So we already have the pi over 4 here. So basically, this will give you the phase factor is whatever makes this qubit 1. So in this case, x1 plus x2 is what makes a qubit 1. So you will end up getting a phase of x1 plus x2. In other words, we can have basically we can summarize the action of t for x equals 1, x equals 0 or 1 as this, right? Essentially, t gate is a way to populate the value of the bit into the phase. So here, t gate, you populate it into the phase, and here I'm intentionally using this equation to. So usually, if for t dagger, we should write a minus in front, right? But here, I'm intentionally writing it as 7 times x1 plus x2 plus x3. So then if you put it all together, you will basically get that the action of the unitary is e to the I pi over 4. You have the first term here, right? And then you have the second term. And then you have the new state. So it will be x1, and then x1 plus x2, and then x1 plus x2 plus x3. So this is one example of how this works out. So I thought it would be helpful to just write this out so you can see how this works, right? So this phi function is just a combination of this kind of terms, and then the function g is just these linear functions. And then if you for some reason you may feel like, okay, this is not good because I want my state to return to my initial state. I don't want, so in many settings it's not ideal to have a quantum circuit that somehow messes up this because if your input is a superposition over x1, x2, and x3, then this kind of not being able to recover the original state will kind of create this undesirable entanglement. Let's say x2, x3 are ancilla qubits, and then you have these messy computations, and then the two register will be entangled, and in many cases you may be interested in uncomputing it. So in that case, you can just repeat this circuit, but in a reverse order, right? So you can make this diagonal without adding any new T gates. So that's why what we're restricting to here is a diagonal unitary, effectively, and maybe to answer the earlier question, I would not consider this a universal quantum computing scheme because it's effectively only the diagonal unitaries. So this function phi deserves a lot more attention because this function essentially tells us something about the number of T gates, and we know from here that T gates are trouble, and we want to minimize them because they make our compilation, they make the quantum circuit more costly. So it's also useful to mention that in hardware, so for quantum error corrected hardware, it takes a lot of resource to implement T gates, a lot more resource for T gates than for Clifford gates. And in in a lot of hardware architecture, for instance, Google's approach so far based on 2D surface code, the way they do it is that to implement a T-gate, usually there's a so-called magic state for T-gate. So you prepare a quantum state such that using this quantum state plus plus Clifford gates and measurement, you can effectively implement a T-gate. So in reality, in the fault-tolerant architecture, one doesn't implement this gate directly. It's actually implemented indirectly by first preparing so-called a resource state or magic state, which is produced through a process called magic state distillation, and that's a very costly process. So once you have the magic state and you have the Clifford gate, then you can effectively implement a T-gate. But that's usually a very costly part for fault-tolerant quantum computation. So minimizing the number of T-gates is actually a big deal. So here I was trying to sort of intuitively explain why we want to minimize the number of T-gates, the sort of practical reason. So this will be an intuitive way to think about it, but the practical reason is that in a fault-tolerant architecture, these are very expensive operations, so we want to minimize them. And the fact that the unitary in this case can be written as this form, the fact that we have this function phi gives us an opportunity to reduce the number of T-gates. The first observation to make about this function phi, so let's call this, so in the literature, this is typically called phase polynomial. And some observation about the phase polynomial is the following. So let's say observations. Right, so one very important observation is that, as it turns out, the same circuit U can have multiple equivalent phase polynomials. So equivalent phi x forms. And this is not really surprising because the phase factor here, right, it wraps around 2 pi. So if you can always add 2 pi to this, right, and it doesn't change anything. So you can add 8, anything that's a multiple of 8 here, and it won't change anything. So you can see that there's this, you can say, gauge freedom if you're a physicist, but there's a degree of freedom in playing around with this phase polynomial. So that, for instance, if you add, so if you take a phase polynomial phi x, and then you add it, you add another function which is always 0 mod 8. So these two are equivalent, right? And then we can invent some function a here, as long as it's always 0 mod 8. We're not changing the unitary that we're implementing. So that's observation number 1, and then observation number 2 is that the number of T-gates, so-called T-count, depends on the number of odd coefficients. In phi x. So this you can see from these relationships. So here the coefficients are odd, right? But imagine if I add something that's 2x1, x2. So this will correspond to a t square. This will correspond to an s gate, right? This basically means I'm adding an s gate here. This will give me a 2x1. So this will give me an even term. So basically any even term, even power of t, will give you identity or something that's still easy to simulate. So z is simulatable with Clifford gates we just showed before, right? So all the even powers of t can somehow be simulated with Clifford gates, and it's only when the power of t is odd that you have a t gate or a t dagger. So that's two observations that you can make, and then the punchline here, right, for this whole series of reasoning is that basically if we want to minimize a t count, it's equivalent to basically minimizing the number of odd coefficients in the phase polynomial. So this is a very big deal because it translates in a quantum compilation problem into a very structured, very specific algebraic problem. I don't know how much you have worked with quantum transpilers. So there's a lot of transpilation heuristics. If you're more mathematically inclined, you might have studied Solovey-Kitaev. But since then, in the past 20 years, there has been many heuristics for compiling arbitrary unitary against a gate set. And in our case, in this particular case with Clifford plus T, we actually have enough insights into how they work to the point where we can actually reduce it to a very structured problem, which is just about the coefficients of some polynomial. So that alone is already quite counterintuitive, quite remarkable. And then what's even more interesting is that this problem turns out to be equivalent to decoding Reed-Muller code. So if you know about error correction or just communications in general, the QR code that we use was based on some variant of either Reed-Muller code or Reed-Solomon code. So these error correction schemes are very prevalent, even in classical communication and computing. And it turns out that in quantum compilation, the problem of minimizing T-gate is equivalent to decode a very well-known type of error correcting code. This equivalence you can find it was described in the work by Amy and Mosca. So I'll just write down the archive number here if you're interested in reading about it more. And this basically sets the stage for some of the quantum compiling work that with Superquantum we're working on automating this part of the pipeline so that all of this can be not just ideas on paper, right? It's actually code that we can run. Yeah.
Would this last for the special case or in general?
This works for the special case when we have the diagonal unitary. But then if you add the Hadamard, so there are there are ways you could decompose a general unitary into this alternating layers of diagonal unitary and then Hadamard and then another diagonal unitary and Hadamard. So this is another paper by the same group of authors based on so-called matroid partitioning. It's not the only way to do it, but at least one way exists. So we're not losing much generality by restricting to the diagonal case. It's just once we have this, it's just that this is the hard part. Like once we have this part figured out, then we can layer on top of it more schemes to handle different types of unitaries. Okay, so I see that we have 16 minutes. So we could do. I have an example, a 4-qubit example where you can see concretely how playing around with phase polynomial will give you fewer T gates. I think that this is the right amount of time for me to go through it, but unless there's any other question. Yeah?
So we want to know the number of odd coefficients, but how do you again represent the even coefficients? You mentioned it, but can you just repeat?
Oh yeah, the even coefficients come from these identities. So t squared is s, t to the 4 is z, and t to the 8 is identity. So let's just say stick with 1 qubit, right? So if we have a single qubit and then we have an S gate, right? Then naturally this is going to give us a phase of e to the I pi over 2 x. Right, so if we start with the initial state x, so x could be 0 or 1, and we apply S gate. Right, this is basically consistent with the definition of theory 1. So here, you can say this is a special case of a phase polynomial where it equals to 2x, right? By our definition, it has to be pi over 4. So in here, you have an even coefficient, and then you can plug in, for instance, z gate, and then you'll get I pi x because z gives you a -1, right? So then you have an even coefficient as well, like of 4. So basically, even coefficients are Clifford gates, and we're not so concerned about Clifford gates. So it should be easy to do. It's to minimize the odd coefficients. That's really the name of the game. Yeah.
Could you maybe explain how what we just learned here, minimize the T count and all of this, play into the larger picture of quantum compilation? And for example, what type of step is it? Would be the equivalent, for example, in a classical compiler? Is it front end, back end, where an optimize the middle end kind of thing? And what is the pipeline of quantum compilation and whatever?
Okay. Yeah. So this would be the second to last stage of quantum compilation. So a very simplistic pipeline would be that if you have a logical circuit, right? So let's just say it's some logical circuit U. Let's say it's Shor's algorithm, right? Someone would write down saying, here's the modular exponentiation, here's the Fourier transform. It's all in the logical circuit. Basically, it says, here's the set of operations I would like to perform. I don't care how you do it, but here's what I want to see happen. And then there's the compilation to Clifford plus T. And then this step is already informed by the hardware architecture. So we would not do this if we didn't know that the hardware runs on the Clifford plus T gate set. This actually is a contested point right now. it has been for the past 10 years almost the default assumption that a fault-tolerant quantum computer should always compile to Clifford plus T. But recently, because there's more development in error correction and there's more ideas for how to build hardware and how to run things on hardware, people start also to wonder about other non-Clifford gates like CCZ. So it turns out that CCZ in some architecture is actually cheaper to run than T gates. So this step is definitely informed by hardware. And then you have some kind of physical execution, right? So this is where you plug in the error correction and all the details. But I would say the decision to run on a hardware was already made before you go to Clifford plus D. So this step is definitely it's a lower level. It's closer to the hardware than a higher level sort of semantic translation or syntactic translation of the compilation. Okay. So yes, if there's no more questions, I'm happy to show a concrete example just to give you a more flavor of how this kind of reduction really happens. Right. So if we consider a 4-qubit circuit, so we start like before, we hit the compiler with the layer of T. And then we have some setup that works with the that works with different pairs of qubits. You can see I'm already repeating myself, like with these block patterns, and those are, if you're quick, you probably have already like computed in your head the terms in the phase polynomial, right? This is x1 plus x2. This is x1 plus x3. This is x1 plus x4, and then I introduce 2 more terms between this. So this is 2 and 3, and then 2 and 4. So this will have a phase polynomial by the way, it's called polynomial because it's a linear function, so technically linear functions are also polynomials. So you can write this as these terms. And so you can see the 1-1 correspondence, right? So x1 is because, so each of the T gate here gives you each one of the terms here. And then you have structures like this, which will give you x1 plus x2. So this C0 computes x1 plus x2, and then this C0 uncomputes it. So that's the missing piece here. Here we don't have uncomputation, right? We just compute x1 plus x2 and we just leave it here. So that's why here we're left with x1 plus x2, but here we make it fully diagonal. But if we just leave this behind, then it's possible that the terms afterwards will change. But here you can kind of see the trick to go back and forth between, if I give you a phase polynomial, you will know how to write a circuit. If I give you a circuit, you know how to write down the phase polynomial. It's basically this kind of translation. So these are the sort of two summation with two, like a pairwise connection. And then because of this 2 pi periodicity that we described before, it turns out that this polynomial can be rewritten equivalently to this other form. Basically, we can write down a form where it's it's all the missing terms from this, like all the possible terms. So this is the missing pairwise term, and then this expression is missing all the three, the group of three terms, and 2, 3, 4, and then finally the term that has all the variables present. So this is equal to this mod 8. You can verify it yourself. It's I guess today you have probably a lot of tools to check that this is true, but there are some identities that you can plug in to see that this is true. But the key is the key thing to notice is that this expression on top has 9 terms, right, with odd coefficients, But this term here, if you count it, 1, 2, 3, 4, 5, 6. So this only has 6 terms with odd coefficients. So that means this circuit can be equivalently transformed into another one with only 6 T-gates, just through this kind of equivalence. And there's something about Reed-Muller code that there's no example I can come up with for 3 qubits. Like 4 qubit is the minimum to demonstrate this kind of reduction. And for more qubits, for general n qubits, you can show. But the general way of playing around with this is essentially decoding a variant of Reed-Muller code. So, but this is a special case that I thought was easy to present. Yep. Okay. So I can conclude here. I think this finishes the whole story of how we go from the basic structures of Pauli operators to Clifford gates, and then to T gates, and then go from Clifford plus T gates to phase polynomial, and then the general way of optimizing the circuit is actually by going deeper into the phase polynomial, and turns out that the math has direct connection with Reed-Muller code. Okay. All right.